Uh, Last week we defined stress, which is a second-order tensor, and to better understand the concept of the tensor, we define a scalar and vector, and we call scalar as a zero-order tensor and vector as first-order tensor. And as you notice that the stress, we need to have a 3x3 component, total 9 components to define a stress, at a one point. And today we will discuss about stress transformations. Well, to better understand the stress transformation, I would like to review the vector transformation first. Okay, what I mean by transformation is that, this is a very important concept. Let's say we have a vector defined at a point. Okay, we have a body and there is one point, let's say point O, and where we have a vector which has this certain direction and amplitude. And now, this vector is a fixed. This vector quantity is a fixed. And let's say to define a vector, what do we need to have? We need to have a coordinate system, right? We need to have a coordinate system, this one or that one, and we definitely need a coordinate system to express this vector. But now, let's say we have a certain component for given coordinate system. Let's say we have this coordinate and vector there. Then this is the x component, that is the y component. Now we have a different coordinate system. But remember, the vector is still same. Vectors are still same. But if we have a different coordinate system, then the component will change, right? Each x directional and y directional component will change. And vector transformation means that there is a relations between each coordinate system. Let's say, again, you have the component in one coordinate system, fx and, for instance, fy, and you have a different coordinate system, and you have a different x and y, I would say x prime and y prime, you have a different component. And there is a relation between fx, fy, and fx prime and y, fy prime. And that is the that relation we call stress transformations. In here, again, this is a vector, and if we define a coordinate system and x and y, then v is simply this much component. This will be a vx and this will be vy. So we call in two-dimensional case, vx and vy. Now, this vector is fixed, and we define a different coordinate system, let's say x prime and y prime. And this vx prime, and vy prime, the components will change. So again, the vector transformation means that vx prime is given as in terms of vx and vy. Let's say we have a rotational angle theta and function of theta, and Vy prime, it will be function of Vx, Vy, and again theta. So let's review that relations, and then let's study about the stress transformations. Okay, again, we have a vector of V here, and X and Y. Okay, this is we call vector transformation. And X and Y coordinate system, and this is the X prime and Y prime. And there is a theta between these two coordinate systems. I'm not going to drive these relations, but this X prime, Vx prime, is given as Vx cosine theta. And then, what is the second term? Vy sine theta, right? And Vy prime is Vx, there's a minus there, and sine theta plus Vy cosine theta. So X prime Vy prime is given as cosine theta, sine theta minus sine theta, and cosine theta Vx Vy. Okay, this is we call vector transformation. And this vector we call a fourth order tensor. Actually, zero order tensor, actually scalar is a zero order tensor. And okay, again, this is a point, a body. And if let's say at 0, we have a temperature, for instance, temperature T will be the same as T prime in different coordinate system. So scalar, the value of a scalar does not change for different coordinate system, but the vector, the component, will vary for different coordinate system. Well, even though each component, this Vx prime and Vy prime, even though the components are changing, the magnitude, we know that Vx prime square plus Vy prime square, this magnitude remains the same, which is called invariant. We will we will study more about the invariant for different tensor. But anyhow, the point here is that the component for each coordinate system have some certain relations in terms of theta between the two coordinate systems. For stress transformation, see, zero-order tensor transformation, which is the scalar and vector, and now the stress transformations. Okay, first we need what is the tensor or stress Okay, this is a continuation from vector transformation, and now we're going to study about this stress transformation. Okay, first of all, what does these stress transformations mean? We need to understand what does it mean. And again, the transformation means that let's say we have a two different coordinate system, and what will be the relations between between those two coordinate system. Let's say we have the O, and where we have a stress. Let's say we have a coordinate system like that, x and y, and where we have a stress, of course that has 9 components, 3 by 3 in 3-dimensional case, and we have a 2 by 2 in 2-dimensional case, where we have a sigma, and now we have a different coordinate system, x and y prime, and we will have the x prime and sigma. What will be the relations? Okay, what will be the relations? Remember that, cosine theta minus sine theta and so on. So similar to that relation, we will have certain relations between this sigma and sigma prime. Again, sigma prime is the stress component in x prime and y prime coordinate system. But here we have to remember that the stress quantities, a stress quantity does not change. Only what changes is that each component. Remember that vector does not change, but component will change. Same here. The stress itself does not change, but the stress component means that that 2 by 2 or 3 by 3 component will change. So what will be the relations between each coordinate system? Then to drive these relations or transformation, first we need to understand again the definition of stress. Okay, we need to understand the definition of stress. Again, okay, just for a two-dimensional case. Let's say we have a stress at here, and we have a cutting plane like this, and there will be a certain if we cut that body into two through that point O, we will have a certain internal force distributions, and which has a certain directions. And this component, that component, we have a coordinate system, and this is called sigma xx, and this is now called sigma yx. Right? Well, yx and xy, now we don't have to distinguish. Since sigma xy and yx, they are same, so we don't have to worry about the two different sub-index. So again, if we cut in y plane, we will have, again, two components. This will be sigma xy and sigma yy. So at that point we have 4 components like that. Now, stress transformation means that we need to define a different coordinate system. Let's say x prime and y prime. So if we cut this body like that, this will be x prime, okay? And now we have this, again, 2 different components, sigma x prime, and this is a sigma x prime and y prime. And perpendicular to this x prime, we will have these y prime directions, and this will be sigma x prime, y prime, and this will be sigma y prime, y prime. Okay? So again, what we gonna drive is that sigma x prime will be given in terms of a sigma xx and certain function, okay, certain function, sigma x prime, sigma xx, sigma yy, sigma xy, and theta. And sigma y prime is again different function, sigma x prime, y prime, a certain function. That relation, again, is called stress transformation. And when we define a stress at here, we used a one coordinate system, x and y, and the stress is always defined at a point. And once we define this stress component and stress, one coordinate system, then stress at for different coordinate system should be given by other component. Anyhow, this is the stress transformations. And now how can we drive this one? Okay, let's put it in this way. Let's say we have what does this stress transformation mean? See, okay, we can always drive relations, and we will definitely drive this relation, but most importantly, you need to understand what does this stress transformation means. Let's consider a simple case where we have a bar subject to an x-directional load like that. Let's say sigma xx. Okay, we have a one-dimensional bar and sigma subject to a sigma xx. Well, of course, sigma xx is defined as the force divided by cross-sectional area. Now we cut here, then I'm sure this should be a sigma xx and sigma xx, and I'm sure we will have a sigma xx to have force equilibrium, right? Force equilibrium. This cutting plane means that, what does it mean? This means that this cutting plane means that we have the x and y coordinate system. Now we define different coordinate system, x and y prime. Well, what does it mean? It means that we have a cross sections inclined this will be a x prime and y prime. Okay, before we define this and let me ask, what kind of forces will distribute at this plane? Actually, this one, the cross sections was A, cross sectional area was A, and now we have this one. This cross-sectional area is A prime. And this one is the theta. And the force should be sigma xx times A, right? Because this cross-sectional area is A, and if we have a sigma xx here, then total force will be sigma xx times A. Now we have a cutting plane which has a certain angle theta, and let me ask, how much force will distribute on this plane? Right, we have to consider, first of all, is it normal or is it parallel to this plane? But regardless of that directions, my question is that how much force will distribute at this plane? Yes, the force should be same, right? Force should be same, and this force should be sigma x times A. That force should be same, right? Because to have a force equilibrium at the left-hand side and the right-hand side, so total force should be same. So total force should be the same. But we want to, by definition, sigma, this force, okay, this force, by definition, we will have the component normal to this plane and parallel to this plane. So this is the, by definition, this will be called sigma x prime, and this will be called sigma x prime, y prime. And how much, what will be this sigma x prime, So anyhow, what we know is that the summation of this one will be same as this much force, right? Same as this much force. Okay, to drive this one, we better consider this way. We have this one. This A prime cross-sectional area has increased. Right? This cross-sectional area A prime is the larger than this A. Right? Again, the total force should be the same between this one and that, but the cross-sectional area has increased. So I would say these distributions, this distributional internal force, this magnitude has decreased because the A prime has increased. So I would say this force, actually the force is the same. So force divided by A prime, okay, force divided by A prime will be the distribute stress, distribute load at this plane in these directions. And then we need to have a component this way and that way. That is the sigma x prime, and this one happen to be a different directions. Okay, so this one will be x prime, y prime. Okay, this is the very important concept to understand stress transformation, and I'm trying to explain what it means using a one-dimensional case. Okay, let's go back to our original questions. Let's say we have the sigma xx uniaxial load, and if we use the xy coordinate system perpendicular to this, orthogonal to same direction here and y perpendicular to this x. Now if we have a cross sections like that, then sigma xx defined over this area A. Now we want to calculate sigma x prime and sigma x prime y prime. But first of all, what do they mean? They mean that first we need to define a prime which has the x prime and y prime like that. And again, total force applied to this inclined plane should be same as before. Right? This cross-sectional A times sigma xx. This should be the same. Total force, total distributed force should be the same, but this area has increased. So distribute load. Total force is the same, but distribute load should be decreased. F divided by A prime. A prime has increased, and we have F divided by A prime. Now and then this distributed load will have two components. One is this way, and the other one is that way. So this sigma x prime, and this is called sigma x prime and y prime. So sigma x prime, y prime is simply called F times A prime, and then what? And then cosine theta. See, this is a theta. Now, sigma x prime, y prime, what is that? A times F over A prime and sine theta. And since this is the y prime direction, there will be a minus here. And again, but how about the relation between A prime and A prime? A prime and A. actually A prime times cosine theta will be A. Right? We have relation between the cross-sectional area A prime and A, which means that A prime has increased by cosine theta. I mean, A divided by cosine theta. And if we put this A prime into here, we will have sigma x prime is given as what? F over A cosine square, and sigma x prime y prime equal minus FA, here sine theta and cosine theta, and sine theta and cosine theta. And what is this? Which was defined as a stress, sigma xx, right? F divided by A was defined as sigma xx. So this is simply sigma xx. So minus, I'm sorry, this is, minus and that simply sigma xx times cosine square, and this is the sigma xx and sine theta and cosine theta. Okay? This is the stress transformations when we have only one component of stress, sigma xx. This is the how we define stress transformation. And as you notice that we have two types of transformation. One is the cross-sectional area. Area has increased or decreased depending on theta. And also we have another transformation, which is this force decompositions. Let's say we have the stress here, and we need to decompose. We have a transformation of force. So we have two transformation. One is the cross-sectional area, and the other one is the force transformations. Cross-sectional area is in fact, a vector, and force is also vector. So that means we have to transform twice. One is for the cross-sectional area, and the second time is the force. So anyhow, as a result, we have sigma x prime is the cosine theta times, sigma xx times cosine square, and sigma x prime y prime cosine xx sine theta and cosine theta. If this is the vector, we would have only cosine theta, right? But pay attention to here, we have twice of cosine theta. And same for here. If this is the vector, then we would have only sine theta, but we have a sine theta and cosine theta. So conceptually, it is a twice result of twice transformations. Okay. Actually, we have a slide express this concept. A bar is loaded by an uniaxial tensile load, which is this one, and bar sigma x. And at this point, we will have a stress defined at this point, and sigma x is like that, Now, how about the inclined section? How much stress we will have? That was the questions, and that was the initial concept why we need to define stress transformation. Now we have a immediate question. Let's consider stress in 2 dimensions. And we have not only x, but also we have y, and also we have x prime, like that, sigma xx, sigma yy, and sigma xy. This much, 3 components together. They are all non-zero. Now let's define stress transformation for these non-zero components. Again, stress transformation means that we need to define a certain sections, and this is the x prime, and this will be the y prime. And to have a force equilibrium, we will have certain distributed load, and that we will have certain component here and certain component here. That's the what distributed force should be in that plane, where we will always drive equation, okay? But again, to understand the concept of stress transformation, in other words, you have to understand what this stress transformation means. This one, again, we have a stress component here, and we have a 2 by 2 defined at this point, and this each component, okay, each component will have in this plane and that plane, and that's what we have, what this component means. And again, this stress, okay, pay attention to here. This stress and that stress is the same. Remember, we have a vector there, vector transformation. Vector was the same, right? Vector remained same, but we have 2 different coordinate systems, and the component will vary, and the vector transformation means that there is a relation between components. And same for here. This stress and that stress is the same, but if we use a different coordinate system, what component we will have? Again, this x prime means that this one and that one, and so on. Speaking of derivation, here is the how we drive that. Again, we have a sigma xy and sigma x prime xy, where instead of sigma xy, we often use tau to denote the shear stress, but it's the same as a sigma xy. Okay, so tau xy. So this is the 2-dimensional stress. Now, if we have a plane which has a direction theta, what kind of stress component we will have at this plane? This is this one and that one. Here we call it sigma n, and here we call it tau n, but this means that sigma nn, sigma n t, and that is the same as sigma x prime and sigma x prime y prime. So anyhow, how do we drive that? Well, the procedure is concept is the same, but the procedure is a little I mean, we have more terms to consider. This triangle subject to this much force, and that this much force, and this much force, and this force and that force, this one and that. So we have many stress or many force applied to this triangle, and to have this triangle in force equilibrium, we have to consider x directional and y directional force equilibrium. Okay, x directional force equilibrium and y directional force equilibrium. Remember that here. Remember here. We had this xx. A should be a let's say, well, there is no component here, but the point was that this much force by this one should be same as the force distributed load times A prime. That should be the same. So here we considered force equilibrium, right? In derivation of this one, we consider the force equilibrium only x directional force. Again, here we also have to consider force equilibrium in x direction and y direction. Now, here is the little detailed derivations. I will use this slide for derivation. Again, we have this is the sigma x, and this is a sigma y, and this is the sigma xy, and this is the sigma xy. To have a force equilibrium, we have to multiply cross-sectional area times distributed load sigma y. So that's why we multiply the cross-sectional area dA times sine theta. And this cross-section, again, we have a dA cosine theta. See, here we define this is the A. Okay, this is the A, just for the convenience. This is the A, then this is the, okay, this is called dA, sorry, dA. And this is the dA times cosine theta. And this is the dA times sine theta. This is the cross-sectional area. And here we have sigma n, actually, which we will derive from this relation. And in this shear term, we have tau or sigma nt, okay, times dA. Again, this cross-sectional area is dA. Now let's consider force equilibrium in x direction, these directions. This direction. I should say in one-dimensional case, I should say force equilibrium in this direction and force distribution in these directions. And this force equilibrium, we will have this derivation. But anyhow, I will further here. I have to say n directional, and we have a t direction. So we have a 1, 2, 3, 4, 5, 6 component of force applied to this triangle, and let's say let's consider force equilibrium. And force equilibrium, we always have two directions, and these directions and that directions. Okay, this is the n direction, and this is a t direction, And let's consider force equilibrium in n direction and t direction. Okay? N direction and t directions. That's what we're going to drive here. So total force in n direction is that sigma, first of all, sigma n times dA. Sigma n, we define sigma n here. So how about the force? Well, we always have to multiply this cross-sectional area. What is the cross-sectional area here? It's a dA. So sigma n times dA is the force according to this stress minus, now let's say we have this stress, and this, and each one would have certain component along these directions. Well, this one will have this much, and this one will have this way, and this way, and so on. So I will draw in parallel to this way. We will decompose this, okay, this way and that way. And this one we will also have this way and that way. And this one will have this much and that much. And this one we will have this much and that much. Okay. Well, so n directional force is, first of all, this much, and this much, and this much, and this much. That is the n directional force. Actually, this is the n directional force. Those forces should be in equilibrium, right? So what is this much? Well, this is the, okay, what is the first? Okay, sigma A, where is the sigma A? Sigma A is this one. How much, what's the magnitude? How much is this one? Well, sigma A times dA cosine theta. See, sigma x dA cosine theta was the force, and now there is the cosine theta. Why is that? Why there is a cosine theta? Well, we need to consider n directional component. So we have to, this one times cosine theta will have this much amplitude, right? Okay. Now, there is a minus. Why there is a minus? Well, this is the positive n, and everything in this direction will have a sign, minus sign there. Sigma y. Well, same for the sigma y. Sigma y was here. Sigma y times dA sine theta, okay, as the force. And this one, we have to multiply sine theta, right? Sine theta. We just decompose this one into this way. And same for same procedure for this tau and this tau. This we have tau, and we have tau here. So this one again, sigma tau x dA sine theta times, I'm sorry, this one is the tau yx dA sine theta, and we have this much component. And same for here. This one, we have this component. So we consider 1, 2, 3, 4 n directional force, and this one needs to be all 0, force equilibrium. And again, well, I just call it sigma. Sigma xy is happen to be same as sigma yx. So consider that relation here and there. Then sigma n, just let's say divide by dA. Divide by dA, we will have a sigma n equal, see here, dA, all dA terms drop out, and sigma n equals sigma x cosine square, sigma y sine square, plus we have one term, first and second term, and twice of sigma xy sine theta and cosine theta. And how about the t-directional force equilibrium? Same procedure. We have a t-directional force. T-directional force is this one, and this one, and this one, and this, and this. So that is the y-directional force. It's the same procedure. This, and we have these relations. Right? This one, we have these relations. Okay. I'll give you 1 minute and memorize these two equations. Now, sigma n, or you can say sigma x prime. This is the x prime and y prime. So sigma x prime, and this is the, let's say, sigma x prime, y prime. And just memorize them. I will have a quiz. So memorize them. 자, 1분의 시간을 줬어요. 이거 기억하게 하는데. And again, we have in terms of a double angle relations, means that cosine square equal 1 plus cosine 2 theta equal twice of cosine 2 theta. Am I right?
Yeah.
And sine theta 1 minus cosine theta, right? And cosine theta and sine theta twice is simply sine 2 theta. That is the double angle relations, and if we use them, we have this one and that. But that is not, there's a next step, but you have to memorize this one and that one. Okay? Now, let's repeat together. Cosine x prime is sigma x, actually xx, Now, x, y, and x prime, y prime. And now let's say x and x prime and y prime. Okay, cosine sigma xx times what? Cosine, right, square plus sigma yy, right, and sine square plus twice sigma xy, okay, sine theta and cosine theta. Okay, very good. And how about the x prime and y prime? Minus and then what? Okay, minus parenthesis and xx minus yy parenthesis close sine theta cosine theta plus sigma xy cosine square minus sine square. Okay, very nice. Can you remember, well, actually there is another term which is the sigma y prime. But anyhow, it's very difficult to memorize them, right? Right? So I will give you a way to memorize it. How to do that? Okay, this is a very much special way to memorize this. Okay, here is a theta there, and here is a theta, right? And always pay attention to cosine theta. Cosine theta, cosine of the angle between two sub-index. Okay, what does it mean? It means that, okay, there is the x prime and this is the x. This is the x prime and this is the x. What is the angle between x prime and x? Theta, right? And cosine of that theta, that is the first one. How about the x prime and x? Again, theta, and we have one more cosine theta. So we have twice of cosine theta. Now, second term, x prime, y. What is the angle between x prime and y? X prime and y. This is the pi over 2, 90 degree minus theta, right? What is the cosine? I said as always theta, cosine. 90 minus theta, what is that? Right, sine theta. That's why x prime and y, there is the 90 minus theta, and cosine of that is the sine theta. And the second term, x prime y, so again sine theta, we have a twice of a sine theta. Now we have the, how about the x prime and x? That is cosine theta, right? How about the angle between x prime and y? Again, the angle is 90 minus theta. Cosine of this angle is a sine theta. We have a sine theta. Okay, why we have a twice of this? Actually, we should have x, yx. And we will have the same sine theta and cosine theta. And this one and that is the same. That's why we have a twice here. Okay? So this is the how you memorize that. And in fact, that's how we drive this relation. Here is the same thing. X prime, let's say x prime x. What is that? Cosine theta, x prime y prime. I'm sorry, x, y prime and x. There is the minus sine theta and so on. This is the relations. Okay, now not shown here, but now how to drive sigma y prime y prime. Well, if we use this triangle, if we use this force equilibrium, we need to consider, see, we have this one, and now we need to consider this way and this much triangles, and here we will have sigma y prime and sigma and we will have all kinds of force equilibrium. Sigma x prime y prime, and that's how we will get this y prime, sigma y prime and y prime. Now let's skip this derivation and just drive these relations using this sub-index. Okay, what will be the here? See, y prime x, what is that? Huh? Right, sine theta, right? And there is another one, y prime and x. Y prime and x. Well, actually, y prime and x is the cosine 90 plus theta, right? Yeah. Which is minus sine theta. Yes. See, always remember whatever angle, cosine of that angle. Cosine of those angle. So that will be minus, and there is another minus sine theta, so plus sine square. And what is the second term? We will have cosine, sigma yy. Well, this is the y prime and y. What's the angle? Right. Theta, and which is the cosine theta, right? And again, there will be a y prime and y, same. So we will have a scale. Now, how about the sigma xy? Well, y prime and x, what is that? Minus, right, sine theta. And how about the y prime and y? Cosine theta. That's why we have a minus here. And again, what is the second term? We have
yx. How about the y prime and y? Cosine theta. How about the y prime and x? Minus cosine theta. I'm sorry, sine theta. So we have a minus. So twice of this one. Right? Okay, that is the relations. See, if we consider only that sub-index, it will be much easier. And see, remember that force equilibrium, the vector transformation, x and y, and x prime and y prime. And same thing, if you have the force vector f, fx and fy, and how about the x prime? Same procedure, just consider index x prime and fx. What is the fx prime and x angles here? Theta, and just cosine of that angle. And how about there will be a second term, which is the fy, and there is the angle x prime and y. What is the angle? X prime and y. This is the 90 minus theta, and cosine of this will give us the sine theta. Well, y prime, same thing. Y prime and x, y prime and x. That is the cosine 90 plus theta, which will be a minus sine theta. And fy, what is the angle between y prime and y? Cosine theta. Right. That's the relation. That is the vector transformation. And as you can see here, this means that a vector component. And vector component is just one time of vector transformation. But stress has a twice index, 2 times of index. So we have a twice of vector transformation. Twice of vector transformation. That is the transformation for stress. So x prime, xx, we have transformation, and we have a second transformation. Okay, so this is the mathematical understanding and derivation of this one using force equilibrium. Well, this is this procedure in x prime force equilibrium and y prime force equilibrium. And this is the one way of derivation. So you need to understand both ways, this force but just, I'm sure, even though you understand this one, you will forget soon. Just understand conceptually. Well, we have a 2-dimensional case, and we have a two force equilibrium. That's all you need to remember, okay? But whenever you want to have this equation, you better use this index, index transformation, which you would not forget. Right? Remember, cosine of whatever angle. Okay? Cosine of whatever angle. And another thing you need to remember is that you have to have all the list, all the components. If you consider 3-dimensional case, let's say x prime, you have xx, xy, yy, xz, yz, sigma zz. 9 components of stress. Okay. Well, in fact, there is only 6 because of stress symmetric. So anyhow, that's how you drive a stress transformation in 3-dimensional case. Concept is the same. And now, okay, let me ask, again, we need to understand why this stress transformation is so important. Why? Why this kind of a stress transformation is so important? Well, later on, we will study further, the purpose of a stress transformation. Let's put it in this way. We have a material, okay? We have a certain material like that. And whenever we apply some force, there is a stress will develop inside. And if we apply force in perpendicular direction like that, take a look at these cross sections of a failure, and plane is exactly perpendicular, right? Why is that? Because this plane has this stress component, and that stress component happens to be the maximum in this plane. But if we apply different force like that, then angle is totally different, right? Why is that? Because that angle has the maximum stress component in that plane. So you should know how to transform the stress depending on the direction of the cross-section. Okay? So understanding of this transformation is quite related to a material failure, and you need to understand material failure whenever you need to design a component, automobile component, automobile engine, airplane structures, whatever you design, you have to understand the failure of a material to have a safe design. Okay? So stress transformation is the most important concept, and which is very much new concept in this solid mechanics, where in bar is subject to a tension and deformation. That is quite similar to a concept as the spring, but this stress transformation concept is quite new to you. Well, you can always extend the concept from vector transformation. That's how you get to this much transformation. But again, you should remember that the stress transformation is needed whenever you want to design a material considering failure. So anyhow, if we consider double angle transformation, this is the relation we will get. Okay, this one. Remember, you have these these relations. If we put this one into here and there, we will get this. Same for here. So this is the secondary notation. But this relation will be, now why we have this a different form? Why we used this kind of a different form? Well, now we can show this transformation graphically, which is called Mohr circle. Very important, and I'm sure you will have this problem in your midterm. Okay, Mohr circle. Stress transformation and Mohr circles is for sure. So anyhow, once you have these expressions, what you can do is that, pay attention to here, you have a certain constant term, sigma x prime, you have a certain constant term plus certain terms times cosine 2 theta, and this is the sine 2 theta. So now theta is gone. Now twice of cosine, twice of sine, cosine is gone. Always cosine, sine, cosine, sine, sine, cosine. But now angle it has been changed to a twice of theta. Okay? Twice of theta. And this one, this relation, again, same as before, but this relation now can be expressed in terms of a circle, graphically. Just a different way of expression. See, we always feel better with the circles rather than equation, right? So we always, so anyhow, this is the graphical expressions, and once you need to understand how to draw this Mohr circle, and this is the x prime, x prime. Well, you go through this procedure. First, you need to define this x and y prime, and see this is the x, xx, xy, and this is the yy x prime, and then this is the x, and this is the x prime and y prime. I will go through this procedure, but you can follow these equations, and once you have, okay, x, y, and this is the center C, okay, this is the center C, and this is the radius, okay, you have a circle. Okay, this is the center, and this is a circle, and this is the how you get the Mohr circle. And this is the brief procedure how to draw Mohr circles. And again, this is nothing new, okay? Nothing new. Same concept, but graphical expression is easier to understand. So this is the how, the total procedure. And this is the example 1 and 2 and 3. We will go through these examples, and there will be homework will be uploaded in our class website. Okay? Okay. And next week, Tuesday, Monday is the holiday, so you will have enough time for homework. So enjoy homework. Okay, see you next Tuesday. Bye.